This very short mini lecture introduces the concept of polarity in chemical bonds and how electronegativity differences can be used to confirm the ionic or covalent character of a bond. Recall that electronegativity is the ability of an atom to attract electrons in a bond towards itself, and that I like to refer to this as the desire of the atom for electrons. This imbalance in the way that electrons are shared between atoms can lead to a bond being ionic, where the electrons are essentially transferred from one atom to the other when the desire for electrons is much stronger in one atom compared to the other. Therefore, the difference in electronegativity can tell us how much ionic or covalent character a bond has, and is another way to classify a bond as ionic or covalent, or somewhere in between. The imbalance also leads to a buildup of negative charge on the more electronegative atom and some leftover positive charge from the nucleus on the less electronegative atom, which gives the bond a polarity with positive and negative poles. The degree of the polarity across the bond depends on the electronegativity difference between the bonded atoms. In the two examples here, the electronegativity difference between a carbon atom and a chlorine atom is relatively small at only 0.5. So this bond is only slightly polar and has a lot of covalent character. But the electronegativity difference between sodium and chlorine is much larger, giving 2.1, representing a bond that is highly polar and has a lot of ionic character. Therefore, we consider chloroform, the molecule on the left, to be a covalent compound, whereas sodium chloride is a well-known ionic compound. There are some general numerical cutoffs for how covalent or ionic character of bonds is classified. Generally, an electronegativity difference that is greater than 1.8 is considered to give such unequal sharing between the atoms that the electrons are essentially transferred from the less electronegative atom to the more electronegative atom, giving an ionic bond. And you'll note that most metal/non-metal pairs will give values of about 1.8 or greater, with the greatest difference possible being 3.3, which represents the difference between the most electronegative element in the periodic table, fluorine, and the least electronegative element in the periodic table, francium. They occur at opposite corners of the periodic table. Differences below 1.8 are considered to represent covalent bonds with some polarity, and below a difference of 0.4 will often say that the polarity is so small that there is essentially equal sharing of the electrons and the bond is nonpolar or purely covalent. Note that this 0.4 cutoff actually comes from the difference between carbon and hydrogen, which is considered to be only slightly polar, and actually in some textbooks it'll be considered a polar covalent bond, but in others they'll consider it a nonpolar bond. For this course, I usually consider carbon-hydrogen bonds to be polar covalent, with every bond below 0.4 difference being nonpolar or purely covalent. Certain types of notation are used to indicate polar covalent bonds. In the example of HCl below, a partial positive charge is indicated with a delta plus symbol highlighted in blue on the hydrogen, the less electronegative element, and a partial negative charge is indicated with a delta minus symbol highlighted in pink on the chlorine, the more electronegative element. There is also an arrow used to indicate the direction in which the electron density is being pulled by the more electronegative element, with a positive sign used on the side where the partial positive charge will be left behind. In order to understand how the partial charges work, consider that when chlorine pulls electron density to the right, it ends up with more negative charge than is needed to balance the positive charge in the chlorine nucleus. So this gives the partial negative charge on the chlorine, indicated by this red region in the electron density picture. On the hydrogen, if it has lost enough electron density so that the positive charge in the hydrogen nucleus is now exposed and no longer balanced by electrons, then there will be an exposed partial positive charge on the left side of this molecule, indicated by this blue region in the electron density picture. These partial charges are strong enough that they will align themselves when placed in a magnetic or electric field, as we see in this picture where the molecules are randomly oriented when no electric field is present, but then they orient themselves along the path of the electric field once the two metal plates take on opposite charges. We can see here that the negative ends are oriented towards the positively charged plates, and the positive ends are oriented towards the negatively charged plates because that's how they would be attracted to each of these metal plates. One final note here is that these partial positive and partial negative charges indicated with these delta symbols or this arrow symbol are both valid ways of indicating what's called a dipole across a bond or in a molecule, where you're trying to indicate the polarity of the bond with these notations. Here we see a little more on how the electron density pictures compare between a nonpolar covalent bond, as in this chlorine molecule, and a polar covalent bond, as in this hydrochloric acid molecule. Note that both the positive and negative partial charges are indicated by different colors in the electron density cloud. And we can see how this electron density cloud has also distorted when we have the one atom pulling more of the electron density towards one side versus the other. So it's very uniform for the nonpolar covalent bond, and we see very uniform color, whereas it's distorted and we see these two distinct colors when we're looking at the polar covalent bond. In this picture, we can see how the electron density cloud becomes even more distorted in an ionic bond, and that there's an even clearer distinction between the colors indicating the positive and negative charges as they become further separated due to the actual transfer of electrons from one atom to the other in the ionic bond that is sodium chloride. In the next chapter, we'll see how the polarity of multiple bonds in a more complex molecule can either combine to give an overall dipole for the molecule, and how the polarity of individual bonds in some structures can actually cancel each other out depending on the geometry of the structure, giving a nonpolar molecule. This concludes the fourth and final mini lecture for Chapter 6. Please note any questions you may have about this material and how it is utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our virtual class meetings, and during that time we will focus more on problem solving for concepts in this chapter.